We're back for part 2 of transmission line theory. And hopefully some of this stuff will start to make sense. So in part 1, I was talking about transmission lines a little bit and about AC phase, voltage and current in a transmission line. And then I jumped ship and I started talking about capacitors. Specifically, this capacitor right here. And you might be thinking to yourself, well, what does a capacitor have to do with a transmission line or an antenna? Trust me, this will all make sense eventually, we hope. But for now, we need to talk about capacitance a little bit more. And then we need to bring in another element of this whole story. So right off the bat, a capacitor is typically drawn as two plates in parallel. That's essentially what a capacitor is. And if we look at this in a circuit, if we draw a battery and we connect that battery to our capacitor, what's essentially happening is when we turn this thing on, we're moving electrons off the plates of this capacitor. So for instance, with one polarity, we're going to stack electrons on one plate and stack holes, for want of a better term, on the other plate. So we're going to steal the electrons off of this plate and we're going to move it around and apply them on this plate. And then if we're reverse polarity, we're going to do just the opposite. We're going to take these electrons that are stacked on this plate, we're going to move them through the circuit and we're going to apply them to this plate. So there'll be a lack of electrons on this plate and an excess of electrons on this plate. And then if we open this circuit up, they'll stay there. So it's almost like a static charge, but it's actually voltage that's just stacked up on the plate until we either create a short circuit or we turn the switch back on, reverse the polarity, or something along those lines. One thing that will never happen on a properly functioning capacitor is you'll never see electrons jumping across these two surfaces. If that happens, we didn't choose a capacitor with a high enough voltage range, because that should never happen. So therefore, there's no continuous DC current through a capacitor. It's impossible. And capacitors are rated in farads, and their rating determines basically how much potential it can store. And typically, with higher AC frequencies, capacitors will move more current through the circuit, because obviously if you have a limited amount of electrons on these plates, whatever they're made of, then there's a limited amount of current that can flow through the circuit. So the bigger the capacitor, the more current that can flow through the circuit. And it can do it at a lower frequency as well. Okay, so that's capacitance. Now the next thing we need to talk about is inductors. I know. It's like, what do inductors have to do with transmission lines and antennas? Well, more than you think. If you have just a straight piece of wire, like this section of wire right here, and as we mentioned in the last episode, if we run a current through that wire, it creates a magnetic field. Essentially what inductance is the resistance to current flow in a conductor. So when we apply voltage on both sides of this piece of wire, there's a momentary resistance to the flow of current in that wire, because that section of wire has to build up a magnetic field. It's a resistance to current flow. We could amplify it by taking a straight conductor and we could wind that straight conductor up into a coil. This essentially amplifies the inductance. So now this coil of wire is capable of storing a lot more magnetic force than a straight piece of wire. Its inductance went up. So it has a higher inductance than a straight piece of wire. Because something like this resists the flow of current initially, if we were to take a voltmeter and put that voltmeter across these two coils and connect it to a battery and flip the switch, what you would see is initially there would be a resistance to current flow. You'd have instant voltage, but no current flow. So in this case, the inductor acts just opposite from a capacitor. In a capacitor, current is ahead of the voltage by a certain amount. If it's a purely capacitive circuit, it'll be ahead of it by 90 degrees. With inductance, it's just the opposite. We have voltage right away, but we don't have current. It takes an amount of time for the current to ramp up in the circuit. So current lags voltage by a certain amount. In a purely inductive circuit, current lags voltage by 90 degrees. So interestingly, these two components work well together. So in the last, we made the determination that if we have a AC waveform with positive voltage, negative voltage, and we apply some capacitance to that circuit, what ends up happening is the current will be ahead of the voltage by a certain amount. If it's purely capacitive, the current will be ahead of the voltage by 90 degrees. With an inductor, the opposite's going to happen. So with an inductor, if we put an inductor in a circuit, an AC circuit, that inductor is going to make the voltage ahead of the current. The current's going to lag the voltage by a certain amount. It could be as much as 90 degrees in a purely inductive circuit. So how does capacitance and inductance play into transmission lines? Well, we know that a radio, typical ham radio, is a 50 ohm device. It transmits into a 50 ohm transmission line into a 50 ohm load. But what we're not dealing with here is resistance. What we're dealing with is another term, reactance. So the resistance is actually impedance. That's the term we're looking for here. It's not resistance, it's impedance. And it's also measured in ohms. And with a transmitter that's 50 ohms, and a transmission line that's 50 ohms, and a load that's 50 ohms, we have 50 ohms impedance on all those devices. We have a 50 ohm transmitter, 50 ohm transmission line, 50 ohm load. And impedance basically is a product of reactance in the transmission line. Reactance is what happens in an AC circuit when you throw in some capacitance or you throw in some inductance. If you model a transmission line, what the models will look like is you'll have two parallel conductors, but the top one is going to have some inductance in it and then capacitance to ground. That's how you model a transmission line. It's series inductance in the wire. Remember, straight inductors resist current flow. And then we have, since it's two plates side by side, it's two conductors side by side, we have some capacitance between those two devices. So we have series inductance and we have shunt capacitance between those two wires, two conductors. And what we're doing is the inductance is going to phase shift voltage ahead of current. And then we have to counter that. So we're going to add in some capacitance, and that's going to shift it back. And then we have some more series inductance. So the series inductance is going to try and shift the phase of our AC waveform, and we have to counter it with capacitance to get it back in phase. That's essentially what a piece of coax or a piece of twin lead is doing. We have characteristic impedance in a transmission line, and it's made up of capacitance and inductance. So one of the first places I noticed this aspect of RF was when taking apart SWR meters and watt meters and taking a peek inside of those devices, or even radios. If you take apart a radio, or better yet, if you take apart a watt meter or an SWR meter and look inside, what you'll typically see is you'll see a little flat disc capacitor right on the SO239, soldered to ground. And that is in there for the reason that we've already talked about, because all of those leads inside of that meter are adding series inductance inside of that device, and we have to counter it with some capacitance. So there'll be a little disc capacitor shunted to ground right at the SO239, or the output of that device. And what we're trying to do is to get that back in phase so that our voltage and our current waveforms are in phase once more. Okay, I hope that makes sense. Now we get to talk about Ohm's law. So when you think of Ohm's law, most of the time people think of just DC. But basically, all Ohm's law is stating is if you have voltage represented by the letter E, and you have current represented by the letter I, and you have resistance represented by the letter R, if you take the current and you divide it into the voltage, it gives you resistance. If you take the resistance and divide it into the voltage, it gives you current. If you take the current, multiply it times the resistance, it will give you the voltage of the circuit. So typically we're talking volts, amps, and ohms. But there's another way we can look at this, because Ohm's law also works for AC circuits. We just have to substitute another letter here, Z. So Z just means total impedance in a circuit. So it's the addition of all the resistive elements, capacitive reactance, and inductive reactance in a circuit. Z is impedance. But the same thing applies. If we take the voltage of a circuit, we divide the current into the voltage, we're going to get impedance. If we take the impedance of the circuit and divide it into the voltage, we're going to get current. If we take current times impedance, it's going to give us the voltage. And now for all your power-hungry types, we take the current, we multiply that times the voltage, and that gives us the power, the watts. So watts is a product of the voltage and the current in a circuit. So if we apply this to a piece of transmission line, what ends up happening is we take the voltage present on that transmission line, we divide it into the current on that transmission line, and it gives us the characteristic impedance of the transmission line. So you can see, if this is how we determine the impedance on a circuit, if we have one of these elements shifted 90 degrees out of phase, it's going to change the impedance of that circuit. So this is where we're headed on this journey of understanding how transmission lines affect the impedance of a circuit. If these elements aren't in phase, if they're not in phase, we don't have the correct impedance on the transmission line. It's going to be off. So let's pretend that this is a 67-foot piece of coax. We're staring at it from the side. And we're transmitting a 14 megahertz signal into that 67-foot piece of coax. There's a full wavelength of RF on that piece of coax. If our transmitter and our antenna are both 50 ohms, and our transmission line has a characteristic impedance of 50 ohms, this wave will travel into the load. From the source into the load, it will travel. And that looks like if you just drop a rock into a pond and watch the ripple move away from the impact into that pond, or if you take a long rope and you tie one end to a tree and you just take the other end and you flick it and you watch the wave go down that rope. This is what's happening. So the wave will travel down the transmission line with very little reflections if everything matches. And something else will happen too. If we take an ohm meter, now I know this is a DVOM, it's not measuring impedance, but let's just pretend for a second that this is a nano VNA. We're going to check anywhere in this waveform. Doesn't matter where. We could check it here. 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 And we could check it here. Along the entire length of this transmission line, it's going to read 50 ohms. And that's because everything is in phase. Because if the voltage and current waveforms are consistently in phase, the relationship between the voltage and current is going to give us a Z that relatively stays the same along that transmission line. No matter where we are on it, it should stay the same. The relationship between voltage and current gives us a Z that's going to be around our target of 50 ohms. So then what happens if we're out of phase? Well, let's say we have a purely capacitive circuit. We're going to take the antenna off of the end of this thing. Now we have a severe mismatch, and our current is going to be ahead of our voltage by 90 degrees. Now we've messed up that relationship. Obviously the impedance is going to change, because if we take our voltage, we divide by our current, we're going to get a Z that's completely different. And interestingly enough, as we advance down this line, it's going to change. So in this 67-foot piece of transmission line, as we check it in different places, it's going to have different impedances. So if we take our same nano VNA and we start checking this thing in different spots, we're going to get a different impedance reading depending where we are on that coax. Now we haven't talked about reflections yet, but that's going to happen, because if we're transmitting into 50 ohms of transmission line and it reaches a target impedance that's not 50 ohms, there's going to be a huge reflection that comes back and creates a standing wave. And that I think we'll save for the next episode. Thanks for watching.